and welcome to another episode of Power Logic. So it has been a while since the last video. So today I'm back with not a competition math problem, but well, something that's kind of well known but not that well known. So let's get started. So on the top we have an integral of e to the x with respect to x. Well, you might say, well, this is so simple, right? It's just something that you guys have learned, like if you guys have taken calculus, it's probably something that's um, coming out the first, which is simply just e to the x plus c, because the derivative of e to the x is e to the x, and we have a plus c, since c, a constant taking derivative, would just be 0. So okay. So, but what about the bottom? Yeah, what about the integral of e to negative x squared dx? Well, something funny is that this integral only makes sense with negative infinity to infinity. Like it's only evaluable to a precise value with this, or else it's not gonna even have a precise value. And if you graph this out, then well, first we know that f of x is equal to f of negative x. So basically, it's symmetrical across the y-axis, and as well, you can see that as x grows larger in the magnitude, then e to negative x squared becomes smaller. So what this means is that it's basically just like a bell curve, which is known as the normal distribution. So would this diverge or would this converge? Well, you might see that, well, it's kind of hard to evaluate this out. You can just try it if you want, but it's really difficult, and well, it's nearly impossible without actually using some of the more advanced techniques. So you might just try integration by parts, but you will see that one can never actually make this to be squishing into a perfect U substitution scenario, and U sub would obviously not work because you have another coefficient of x, right? And obviously not trig substitution. So how are we gonna start with this problem? Well, we square this first. The first step is actually really difficult. Well, because so we square this first, and it's really difficult because, well, how would we even think this at the first place? Now you might be saying, well, how does that help? You square it, and nothing changes. You still have to evaluate the inside to evaluate the outside, right? Well, no. Now we can actually what? Now we can actually turn this into actually two integrals. So it's e to negative x squared, and we have e to the negative y squared dy. Well, why does this work? Well, because you're just using a different variable, right? So different variable, then this basically just means that your integration has a function of y, but it's exactly the same function, so the error wouldn't change. So we can just make a variable that's same but not the same, right? Now what? Now how are we going to continue? Well, we can actually combine these. So we can combine these into two integrals from negative infinity to infinity. Let me just copy this. So we can actually copy, right? So we can actually dx dy. So basically we combine it into this form. Now you might be asking, well, why this form? Why can't you just make two variables and combine them into this? And what does this even mean, right? So, well, basically you're evaluating the integral inside, and you're just ignoring y as a constant, and then you're evaluating the integral that's outside. So let's define, well, we have an f of x, and we also have an f of y. So let's say we have f of x and f of y. Then we want to show that the integral c to d of dx f of y dy is equal to combined. It's equal to the integral from a to b and the integral of from c to d of f of x, f of y, dx, dy. Well, let me just call this to be g of y. So we want to show that this works. And if this one actually holds, then we know that this would obviously work because this is basically just a special case of this general theorem. So how are we gonna do this? Well, let g of y be equal to integral, be the indefinite integral of g of y dy, and f of x be equal to the integral of the indefinite integral of f of x dx. Then what's the left side? Then the left side is simply what? It's simply just, well, f of b minus f of a, right? Or f of b minus f of a times g of b minus g of d minus g of c. So on and so forth. Pretty simple. Well, because basically you just evaluate separately, right? Well, what's the right hand side? Well, the concept of double integral is basically first you evaluate this inner integral. So this inner integral from this integral from c to d to this dx. So essentially you're just treating g of y as a constant, and then you simply just evaluate this out. Okay, so what is this? The right hand side, well, is basically the integral from a to b of f of b minus f of a g of y dy, right? Or can you try to figure out why is that? Well, if you're curious, then please pause this video for a while and maybe try to figure out like why is this. But I think it's pretty straightforward. So since you're treating y as a constant, and g of y is also a constant with respect to x, right? So now you're just simply evaluating g of y times the integral from c to d of f of x dx, and that is simply just big f of x, right? Well, actually, sorry, I've written it into a wrong order here. Here should be from a to b, from c to d. Make sure to pair the integral with this variable. So now, now we're just doing the same thing, right? Then after evaluating, now this f of b minus f of a is a constant with respect to, well, not only y but also x now. But now f of b minus f of a, you can take it out. So this is just equal to f of b minus f of a times the integral from c to d of g of y dy, right? So notice I'm just making this to be simpler so that you guys can understand it more clearly. So now this one just, well, becomes the big G of D minus big G of C times, well, it's multiplied by f of b minus f of a. And we're basically done. And we're basically done here. So yeah, so the proof is complete, and now we know that this one actually holds. Now you might say, well, what now? Right? You have this thing, or you have this x squared plus y squared and exponent and dx dy. You're just making it more complicated by making one more variable out. Well, not exactly. So here, well, you see the exponent x squared plus y squared. Does that sound a bit familiar or ring a bell in your mind? Well, yeah. So x squared plus y squared is simply like really similar to the Pythagorean theorem, except we have an r squared, right? Well, except we have a c squared, and x squared plus y squared equals r squared is actually the equation of a circle. So this actually reminds us to use the polar coordinates. Aha, polar coordinates. Let me just make this a little bit formal. Polar coordinates. So what does that tell us? Well, since x squared plus y squared is equal to r squared, then we let x be equal to r times cosine of theta, y be equal to r times sine of theta, right? Then x squared plus y squared is simply just r squared times sine squared theta plus cosine squared theta, which is r squared. So basically we're just gonna do this kind of substitution here. Now we have to not only consider about the variable, but also consider about this integration part and also this. So now what is the integrand? Well, we know the integrand changes to be e to negative r squared, but what about the bounds? The bounds of integration, how is that going to change? So, well, if we're, yeah, so let's first try to figure out what the variable of integration would be. So first we know that it's going to be the end of e to the negative r squared, right? Negative r squared. And what's the dx dy representing? So now let's think about a circle. Okay, so we have like some kind of graph here, and we have a circle. Now let's just now notice that each part, or each small part of the circumference on the circle, is simply created by the two radius and also a small angle in between, and we can call that to be delta theta. Then as the theta goes smaller and smaller, then what we notice is that, well, it literally just becomes a perfect circle. No, it literally just becomes a perfect straight line, right? Now we consider dr, like a little part change in the radius. That's also a straight line. So then dx dy is simply just a small piece of area. So basically this is just integrating with respect to a 2D region, right? Now we have r, well, r times theta is the length of the arc. So as the arc goes really small, then r times d theta is simply the length of the arc, and the dr is simply the small change in radius. So essentially, then the bound becomes r dr d theta, which theta is simply just the angle between the radius to find the length of the arc. Now what is the bound of integration? or e to the negative r squared, well, so r can just be as long as it wants, right? So from 0 to infinity. Now what about the outside bound? Well, theta goes from 0 to 2 pi. So simply from 0 to 2 pi, right? Since we're going around a circle. So now we're ready to evaluate. Now here, r times e to the negative r squared. Now we can just use u sub, right? Let u be equal to negative x squared. Then du is equal to negative 2x, so negative 1/2. So negative 1/2 times u du is equal to so if u is x squared, then du is equal to negative 2x dx, and so 1/2 du is equal to x dx, right? Or should I just use the r here? Sorry. So r dr, this integral transforms to negative 1/2 then du is negative 2r. Well, actually, we'll let u be equal to the r squared. 2r, so 1/2 u. Wait, no. Yeah, let u is negative r squared, then du is negative 2r dr. So negative 1/2, so negative 1/2 e to u, but we have to change it to be negative infinity here. Now from here, well, we simply just have the integral from 0 to 2 pi, from 0 to 2 pi of, well, 1/2 e to the 0 minus 0. Since 0, well, e to the negative infinity would just be equal to 0. So d theta which is equal to the integral from 0 to 2 pi of 1/2 d theta. Now this one just simply evaluates to 1/2 times 2 pi minus 0. This is equal to pi. Now we're finally into our last step, which is, well, because we squared it first, so essentially we have of e to the negative square dx is equal to pi square is equal to pi. Yeah, now we know that area is definitely positive, right? Since it's going from left to the right, and it's always above. So therefore, the answer is just simply square root of pi, and we are finally done with this problem. So thank you for watching, hope you enjoyed, and I'll see you in the next video. Goodbye.